This
And
conference will
welcome back
now
to a
be
fresh
recorded.
session of Regression modeling. Okay, so before I start off the session discussions, just a couple of queries, a couple of clarifications. Number one, is my voice audible and is my screen visible? Can you hear me and see my screen? Hello, am I audible, guys? Can you hear me? Great. Okay. So let's do a very quick recapitulation of the stuff that we were discussing in the last class, and from there we will take it up. Okay, so good afternoon, everyone, and let's get started. So in the last session, we were discussing the classical linear regression model. Right? And when I talk about the classical linear regression model, so it's the linear regression model that we are reminded of, right? And in the last session, what we had done was we had been talking about the properties of the best fit line, right? And we talked about the key aspects of these properties, right? So basically, our objective of the simple linear regression model was estimate the parameters, alpha and beta, using the estimated values of using the estimated statistic alpha hat and beta hat, such that the sum squares of the errors are minimized, right? So what we saw was that first we estimated the alpha hat and the beta hat. From there we put them into the estimated regression equation. From there we got the best fit regression line, and then in the last session we talked about the properties of the best fit regression line. So when we talk about the properties of the best fit regression line, one of the important things that we get to see is that the the estimators, right, or the beta hats, have to be best linear unbiased estimator, right? So talking about the best estimator means the variance of the estimator has to be the minimum among the class of all unbiased estimators, and the estimator has to be linear in nature. So also one thing that we saw was we came across certain implications. One of the very important implications from the best linear unbiased estimator is that we saw that it was the non-stochasticity of the estimators which ensured that the estimators were kind of linear, right? Now, the next thing that we also looked into was the testing of the hypothesis, right? So we looked into how exactly is it that this beta hat can be tested and so on, right? So we looked into the beta hat, we looked into ensuring that the error terms were white noise and so on, right? Fine. So there, the next question that comes out to us over here was that how do we assess? So basically, what we looked into was that how do we detect the white noise. So basically what we saw was that what do we do in order to detect that the residue is a white noise? What is the implication of the errors being white noise, and how to test them, and what are the properties that alpha hat and beta hat should have, and how and what are those assumptions which ensures that the model estimates are the best linear unbiased estimators, right? Okay. So in today's discussion, we will focus on assessing the goodness of fit of a linear regression model. So we'll look into so now the goodness of fit is described in two terms or in two ways. One of the goodness of fit is to assess the statistical significance of the parameter estimates, right? Of parameter estimators. That is the beta hat and the alpha hat. The next thing that we try to look into over here is the overall fit of the model. So how does the model fit on the whole? So what does this mean? What does testing the statistical significance of the parameter estimates imply? Why do we need to do this testing? Why do we need to assess the overall goodness of fit of the model? What are the so what do these each of these tests these set of tests would imply? What are the things that they would capture about the performance of the model, right? So in today's discussion, we'll start off by talking about the statistical significance of the parameter estimators. And to do this, we will use the t-test. Now, the question that comes out over here is that why do we need to use linear regression? Why is linear regression used, first of all? Now, in linear regression, what I am trying to do is I'm trying to estimate the value of yi using the parameter estimates alpha hat and beta hat. And what does beta hat denote? So beta hat denotes the slope coefficient. It shows the element of responsiveness that yi hat would have to 1 unit change in xi. So what we are trying to actually understand in the first place is that does xi cause yi? This is the causality test. So what is the question that we are trying to address right at the beginning when we try to assess the goodness of fit of the model? So the first question that we try to address over here is that does xi cause yi? Now when I say does xi cause yi, right? So one of the parts that comes into question is that do they significantly cause yi? So does, when I say this cause, it means does a variation, does a unit variation in xi does a unit variation in xi significantly explain significantly explain a variation in yi? significantly explain the variations in y. So what it also implies is that can xi explain the variations in yi, right? So this is the first and the biggest question that we need to address when we are kind of developing a linear regression model. So how do we do this? So to do this, we need to develop a statistical test. So what we need to do over here is we need to develop a statistical test. And what will be that statistical test? That statistical test will be a beta test or will be a simple t-test, a statistical test. And when I talk about developing the statistical test, that test is nothing but that develops the test. So the first question that we need to address over here is how does the test work in this? So how would the hypothesis for this test be framed over here? How would I frame the test hypothesis? So the easiest, so one of the, so basic idea over here is that beta equal to 0 versus the alternate hypothesis is beta not equal to 0. So the first question that comes out over here is, so that we are trying to address over here is, we are trying to create, so our conjecture over here is that beta, right, is, so the null hypothesis is that beta is equal to 0. So the estimated value of beta that you can see over here, even if it is a value which is not different from 0, is nothing significantly different from 0. All it means is that yes, there is a value, but that beta is an observed beta. It is not statistically significant. Versus the alternate hypothesis is that beta is not equal to 0. So it means that the value over there that I can see for beta is a statistically significant value, right? So this is precisely what the test hypothesis is. Now the question that comes out over here. So just to refresh once again. So this beta equal to 0 talks about the observed causality. Observed but not a statistically significant causality. But not a significant causality. So over here, So beta not equal to 0. This is a statistically significant causality. So when I am trying to assess this, that whether the estimated value of beta hat that I have with me is statistically significant or not, right? So that is why I am trying to do a mean difference. So I'm trying to do the t-test. Now, why can I do the t-test over here? Because I know that the beta hats are normally distributed. And what is the distribution of beta hat? The distribution of beta hat was discussed over here. So beta hat follows a normal distribution with a mean beta and a standard error, and a variance of beta hat is this, and this variance of beta hat that I have over here is the best, is the best variance, that is, it is the most, the minimum variance amongst class of unbiased estimators, right? So over here what I have is a statistical significance. The statistical significance. So now what we need to do over here is we need to create the test statistic. How do we create the test statistic over here? So when I'm creating the t-test, right? So we know that we are trying to understand that whether the deviation of the beta hat is substantially far away from 0 or not, right? So if you think about it as a graph, as a line, right? So let's say this is the line. So this is 0, right? And say these are all the beta hat values. So this is beta hat in one sample. So this is beta hat in the second sample. So this is beta hat in the third sample. Let's say it's arranged like this. Right. Now you see that if I choose this, if this is the beta hat value, right, that I have obtained in my estimate. Now this is relatively closer to 0. Hence, if I choose this estimate as the beta hat value, I will have the highest probability of committing the type 1 error. Now the probability of committing the type 1 error will be relatively lower for beta 2, and it would be the least for beta 3, because beta 3 hat is the farthest away from from 0. So all we need to understand is that how far is beta hat from this 0, right? Why 0? Because what I'm saying is that under the null hypothesis, beta is 0. So all I want to understand is that the farther away the beta hat coefficient is from that 0 value, the higher are the chances of beta hat being significant, and lower are the p values. A lower would be the actual probability of committing the type 1 error, right? So is this logic clear to everyone?
Sir, I have a question that t-test we are doing for comparing the samples or variables.
No, no. I am doing the t-test to assess whether the beta or the beta coefficient is significantly different from 0 or not, right? So I
Yes,
need
sir, but
to,
I understand that. So,
Mhm.
but the question is, are we comparing t-test for comparing the two samples or the two variables that they are both are same or not?
No, 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 no. We are not comparing whether the two variables are same or not. All we are comparing is that does X explain Y? Because if beta hat is not statistically significant, then it means that Xi does not significantly impact or explain the variations in Yi. So we need to ensure, let's
Okay,
say,
understood, sir.
so I'll just give you a quick example. So let's say Yi is 10 plus 0.002 xi. So one thing you can see is that every unit change in xi, right? Y will change by y will increase by 0.002 units, right? Now the question that comes out here is that is this impact that xi is creating on yi, is this something which is significantly different from zero or not, right? So, so if I draw this graph over here, say this is 0 and this is 0.002, then is this difference of beta hat from 0, is this a significant difference or not, right? So that is what we are trying to assess, because if the impact that xi is having on yi, if that is not a significant value, then I will not be keeping xi in my model. I'll not be keeping any variables in my model which has an observed impact on yi. If that, I will only retain it back if it has a statistically significant impact on the dependent variable, right? So that is why I'm doing the t-test over here. So the basic concept of t-test over here will be, now we know how to define the t-stat, right? So t-stat is beta hat minus expected value of beta hat divided by the standard error of beta hat. Now, in the t-test, one thing that we saw was that we were trying to understand whether there is a statistically significant difference between an estimator and a parameter. And when we are doing this, when we are trying to assess whether the difference between the two is statistically significant or not, or whether the difference is actually significant difference or not, then we need to look into the difference relative to the overall variation in the beta hat, right? Or in that particular, so we need to look into the difference relative to the overall variation in the sampling distribution. Now, since I'm trying to explore, assess whether beta hat is equal to 0 or not, or whether it is statistically significantly different from 0 or not, so the t-stat will be beta hat minus expected value of beta hat. Now we know that beta hat is an unbiased estimator, right? Now, since beta hat is an unbiased estimator, we have seen that expected value of beta hat is equal to beta. So therefore, what we have is,
Can you please repeat the last sentence?
sorry, which part?
Could you please repeat the last sentence?
Okay. So what I am saying is that we know that, or what we have seen from the last sessions, the discussion in the last session, that beta hat is an unbiased estimator for beta. Now, because beta hat is an unbiased estimator for beta, therefore, we have seen in the last session and also have proved that that expected value of beta hat is equal to beta, right? So this expected value of beta hat becomes beta. Now, what is the value of the beta under null hypothesis? Because whenever we are trying to create a test statistic and take a test decision, we are trying to do it with reference to the null hypothesis. So under H0, right? So under the null hypothesis, under H0, beta is equal to 0. Now, because beta will be equal to 0 over here under the null hypothesis, the t-test statistic is beta hat divided by the standard error of beta hat. Beta hat divided by the standard error of. Yes, questions. Any questions up to this point? Okay, fine. So T is beta hat divided by standard error of beta hat. So now the next thing. So now think about this T statistic. Now how are we trying to, or how can we interpret this? Now the way we can interpret this is as follows. So what I'll say is, that further the beta hat is from 0, because this beta hat is nothing but minus 0. The further the beta hat is from 0 relative to the standard error of beta hat, or relative to the overall variation in the sampling distribution of beta hat, the higher is the value of the test statistic. Now, higher the value of the test statistic is, the lower would be the probability of committing a type 1 error by considering the distance as significant. So, if you think about it, the probability of committing the type 1 error that you would have in this zone will be much higher than the probability that you will have in this zone, right? And that probability will be lower, or probability of committing the type 1 error will be lower in this zone. So further the beta hat goes away from 0, the larger is the t, the higher is the value of the t stat, and hence lower would be the actual probability of committing the type 1 error. So one thing that we can see over here is, so one relationship that we can clearly state out here is, so if t is higher, then the p-value will start getting lower. Right? And lower the p-value will be, right? So then greater will be the chances of p less than 0.05 to be satisfied. Now we are conducting this test at a level of significance of 5%. So this is the default level of significance that we generally work with. We can say that, okay, fine. So what we can say is that, okay, at a 5% level of significance, the test is conducted. So basically, once I have created this t statistic, right, the p-value will get computed. And always lower the p-value, the greater are the chances of the account of the test statistic of being of the null hypothesis being rejected. So p-value is less than 0.05, or let's say put it at less, if p is less than alpha, then 80 is rejected at alpha level of significance. At alpha level of significance.
Sir, here P is probability of committing type 1 error.
The actual probability of committing the type 1 error in the model.
Yeah.
And alpha is the benchmark level of committing the type 1 error. So alpha specifies the maximum amount of type 1 error that I am willing to have. And P signifies the actual probability of committing the type 1 error.
Hello.
Yeah, tell me.
Probability of committing the type 1 error means rejecting the null hypothesis.
Rejecting the null hypothesis given that it is true. So your type 1 error will be your type 1 error will be the probability of committing rejecting H0.
Means
Now, if you're
beta is null and we are mistakenly considering it is
correct,
significant.
as significant, correct, given H0 is true. Right, so this is the probability of rejecting H0 given H0 is right. So the entire idea over here is, so to assess whether a particular variable has a statistically significant uh, relationship with y, so does X significantly explain y, we do the t-test, right? The null hypothesis of the t-test is beta equal to 0 versus beta not equal to 0. The T is the test statistic, and p less than, so if the probability, if the exact probability or the actual probability of committing the type 1 error is less than the benchmark level, then benchmark level of committing the type 1 error, then the null hypothesis is rejected at a alpha level of significance. Clear? So any questions up to this point?
P is less than alpha is satisfying the level of significance. Not
Sorry, I just missed out what you said. Will you repeat again?
Can you please repeat this? P is less than alpha. Uh, H naught is at And
is
H0 will certify.
rejected at alpha level of significance.
Sorry, H0 is
Rejected.
rejected the
REJ.
level. Okay, and if we are rejecting the level of significance, then
No, we don't reject the level of significance. We conduct the test at a specified level of significance. So level of significance is an exogenously provided level of type 1 error that we can formulate, right? Let's say 5%. So it means that I can allow 5% of p-value of up to 5%. Now, if the actual probability of committing the type 1 error when I do the test exceeds this 5%, then I will say that I will not risk rejecting the null hypothesis because my actual probability of committing the type 1 error is much more than 5%. Hence, what I do is I will not reject the null hypothesis, I will accept it. Now, if the actual probability of committing the type 1 error is less than the specified level, then I will reject the null hypothesis, saying that, okay, I can reject the null hypothesis over here because I know that the actual probability of type 1 error is much lower than the, so that is much lower than the allowable type 1 because it's within the range. We can say that yes, we can accept the alternate hypothesis. So whether you are accepting or rejecting a null hypothesis depends on the actual probability of committing the type 1 error relative to the benchmark level, right?
So beta is equal to 0.02. What will you take it? Null hypothesis or t-test will tell us?
Yes, the test will tell us whether this 0.002 is a statistically significant difference or not. So over here beta hat is 0.002. So the expected value of 0.002 divided by the standard error of beta hat, you will get the t statistic. At the t, you will get a corresponding probability of committing the type 1 error. And when you get that probability of committing the type 1 error, you compare it to the alpha. So p less than alpha. So if I see that the p-value that I have computed is less than alpha, less than 0.05, I'll reject the null hypothesis. So in SAS, when we run the proper statement, this table of variables along with their statistic, their computed p-values is generated. And all you need to do is you need to check whether it is less than your level of significance or not, and take your decision that which is the variable that you are going to enter, which is the one that you are not going to keep that. So all these outputs are generated as a part of the SAS procedure. So we need not separately count out each of these steps. But what we are trying to do over here is we are trying to understand the backend algorithm that goes on when we run the proper statement. So when the output comes up, we would understand how to exactly interpret the relevant output, right? Yeah. So are we clear on this? Just think about it. Think about this, whatever we have talked about. So this provides, so over here, this is the first part. We talk about the statistical significance of the parameters. So the first thing that you do in order to assess the goodness of fit of a regression model is to understand whether the exercise which are gone in are those exercises which would help us explain the variations in Y. Right?
right.
Yeah. Good.
Okay, for t-test, it is a beta cap upon standard error of beta cap. So,
I
from where we will get these standard error? Let's say the value of t is
Yeah, so
uh,
when you run the SAS, when you run the PropCorrect output, right? So the T statistic estimate, the standard error, the parameter estimate. So the parameter estimate, the standard error, the T statistic, and the p-values will be generated when you run the PropCorrect statement.
so.
All you need to do is you need to specify the name of the reference data set where on which we'll be running the regression analysis, the name of the dependent and the independent variables, and SAS will give you all the relevant figures.
Right. So we'll be getting the p-value from the
You get
regression.
everything. All the outputs will come out in one single box. All you need to
So wait,
specify the dataset name, the dependent and the independent variable, and all other quantities or whatever features you want.
so how does this p-value, what is the significance of this p-value? Because we are seeing only the p-value. If it is less than 0.05, then it is, you know, we will reject the null hypothesis.
Uh-huh.
So
Yeah.
what is the
So I did not get your
significance of
question, Shashi.
no? So here you are saying when p-value is less than 0.05, we will reject the null hypothesis.
Right.
I want to understand where does this, what is the significance of p-value? Why are we calculating value?
So why are we calculating p-value and also this is already which we have discussed when we were doing the testing hypothesis discussions, right? So if you go through those recordings, Shashank, you will be able to get an idea as to why we are computing the p-values. So these are discussions that have already been done, right? Now we are applying those discussions into understand how to assess the goodness of fit of the of a linear regression model. But just to refresh the p-value, so whenever you are computing anything, right, so you need to ensure that, so what we try to do is we always try to minimize the type 1 error. Now if we see that we run our model actually has a higher probability of committing a type 1 error relative to the zero, relative to the level of significance, or relative to the uh, you know relative to a certain cutoff value of the probability of type 1 error, then we do not risk of considering the value as significant. We automatically accept the null hypothesis to be conservative, which ensures that the so whatever the quantity is that is statistically insignificant. So basically the idea of p-value is to check the chances of committing a type 1 error if you were to consider something, a statistical quantity, as statistically significant. So p-value tries to answer the following question: what is the actual probability of committing a type 1 error in my model if I consider this beta hat to be statistically significant? Now, if I see that the actual chances of committing this type 1 error is actually very high relative to the cutoff value, then I will not risk, I'll not take the risk of considering this as statistically significant. I will deem this as observed variation and I'll accept the null hypothesis. And I'll say that whatever coefficient this beta hat has over here is just an observed coefficient. It is nothing significantly different from zero. So that would vis-a-vis imply that the impact that xi has on yi is nothing statistically significant. Hence, that variable will not be used in the model. So the p-value plays the role of assessing the chances of this type 1 error which can be actually committed in the model. So by comparing this with the cutoff value, you can minimize these chances of type 1 error. Right?
What is the significance of t-value? T-test. Okay, t-test is true.
So Shashank, these are concepts which have already been discussed. Okay. So just go back and kind of go through those recordings. You will get a detailed description of discussion on t-test, because before starting linear regression, we had discussed all these. We had discussed t-test, f-tests, ANOVA, mean difference tests, and everything. So those are already discussed and recorded. So just go through those recordings. I think you would be able to refresh. So t-test is used to assess the significance of a parameter, right? So the entire idea of t-test is to ensure whether a null hypothesis, whether let's say for over here beta is equal to 0. So how far is beta hat actually from 0 relative to the overall variation in beta hat, right? So for that concept, you need to understand what a sampling distribution is. So all these concepts have been discussed previously, right? Now, in the interest of time, I cannot kind of reiterate the entire thing. It would take us a lot of time. So what you do is you just go back to those recordings, go through them, see if you have any challenges in understanding them, and then get back to me so we can sit down over a call and we can discuss your doubts, right?
All right.
Okay. So, so the first thing, so over here,
Tanmay, just
yeah, tell me.
one question. So then here we are doing this type 1 test. So I mean we are checking this type 1 error. So we don't go for checking type 2 error as well when it
No,
comes to
no.
validation.
So type 2 error we look into when we want to look into the power of a test, right? So as far as testing for the significance of testing hypothesis is concerned, we are always more concerned about the type 1 error. The reason is because let's say if a type 1 error is committed in a model, what does that mean? It means that there is actually a irrelevant variable which is being incorporated into your model, right? Now, this variable will lose its its explanatory capacity more over a period of time, over a longer period of time. Now, when that happens, then your model performance will start dwindling. So, we should always be more concerned about removing the irrelevant variables rather than incorporating them in your model. It unnecessarily burdens your model. It reduces the degrees of freedom in your model. So that's primarily the reason as to why the type 1 error is of more importance compared to a type 2 error. Now, type 2 error concerns around the alternate hypothesis, right? Now,
Yes.
now type 2 error, right? So 1 minus the probability of type 2 error becomes the power of a test. So lower the type 2 error is, the higher is considered to be the power of the test. So, but for assessing significance, insignificance, or for modeling purpose, for developing any kind of models or causality frameworks, it is always type 1 error. Because when you are developing this causality framework, it is more important to remove the redundant components rather than have all the active component in that. Now, it may be the case that you have missed out a important variable, significant variable from your model. That you can capture by looking into autocorrelation and heteroscedasticity. But if you have a redundant variable in your model, you cannot capture it through your, so you would not be in a position to capture that, right? And over a period of time, the model performance is going to dwindle out, right? So that's the reason why type 1 error becomes mandatory.
Okay, so when it comes to regulatory, say when it comes to advisory level,
It is
do
always
do
type 1 error. It's always type 1 error.
type 1
So
always?
whenever you are doing any statistical testing, you look into the type 1.
Okay. But
Right, because
if
you,
I
uh-huh.
yeah, so like my question is, so see, as a regulator, I would like to check that whether the model is well conservative or not, as per the capital requirements, right?
Hmm.
If model is less conservative, I
No, it's
I would
not
be
about being less conservative. It's not about being less conservative. It's about what, see, if you are not incorporate something important, that will get reflected somewhere. Where will it get reflected? In the model accuracy, right? So when you do the model accuracy, that's the reason why you divide it into three parts, your data into three parts: out of time data, out of sample, and development data. So that you develop your model and then you test that accuracy across multiple samples, right? So, so if there is something which is missed out, something important, some important variable which has not been captured in the model, then what will happen? Your accuracy of the model will vary across the samples, right? So your model will not actually come, your predicted values will not come close to the actual values. That is the reason. So that's when you can capture what you have, what you should have incorporated, but you have not incorporated. Now assume the opposite situation. You have incorporated something which is redundant, but you have still incorporated into your model. That just overburdens your model. So what will happen is when you run your accuracy, that variable alone is not going to contribute anything, but it will show your model accuracy similar across. But if you run the model, if you run that model, your model across multiple samples, right? You will see that that insignificant variable which you had used in your development data, that turns out to be insignificant in your out of sample data, in your recent out of time data, in your historical out of time data, right? So it is more important to prevent unnecessary or redundant model variables from entering into the model rather than capturing those variables which could have been incorporated. Because if you have not incorporated something important, you can capture that at any stage of the model development exercise. But if there is a redundant stuff which has gone into your model and that has not been removed, it can create unnecessary issues in model stability going forward, right? So that is why your type 1 error anytime remains important over type 2 error.
Got it. Sunil, will it be right to say that type 1 error is overestimating the risk and type 2 error is underestimating the risk? No?
Type 1 or type 2 error has nothing to do with this. First of
It is
all,
just about the
they are
variables.
statistical concepts.
Got it, got it.
All they tell you is that if you consider a variable or a coefficient as significant, what are the chances that you are actually rejecting a true null hypothesis? So what are the chances that you are actually considering something insignificant as significant? That is
Yeah,
all what type 1 error tells you. So it has nothing to do with risk. So
yeah,
risk
okay.
is risk. So your risk will be captured by your variables. To ensure how accurately your variables capture risk, that's where you need to have an idea of the type
Hmm, got it. Yeah, thanks.
1, right? Okay, great. So, so over here we have talked about the statistical significance of the parameters. So over here I have talked about that, okay, y, there is yi hat equals to alpha hat plus beta hat xi. If beta hat is statistically significant at a given level of significance, then I will say that xi is an important variable explaining yi or explaining the variations in yi in the dependent variable. Now the question that comes out over here is, so we need to extend this to something. So till now I've been mostly been talking about a simple linear regression model where there is only one explanatory variable, right? Now what I'm doing is I'm extending this to multiple variables. Let's say there are many variables in the model, so which is mostly the case. So you start off with 1,700, 700 or 1,000 variables, and then you gradually trickle down to reach the 6 to 7 top variables which explain your dependent variable, right? Or which captures the maximum variation in your dependent variable. So over here, when there are multiple variables, right, many variables, that is where association between variables becomes very important, right? So some variable tend to be function of other variables. Let's say in a model, right, you have a variable light. So I'm just using an arbitrary example. Uh, you have variable like employees compensation. Okay. So let's talk about variables like this. Employee compensation. Let's say employee compensation. The next that we have is bonus. Bonus incentives. Now let's say that all these three enter into a model to describe the employee satisfaction. So then what do you see over here? So you have employee compensation, you have bonuses, you have incentives. Now the question that comes out over here is that if I use these three variables in the model, there will be a challenge. And that challenge is that these variables will be linearly related to each other. They will be linearly related. They are linearly related to each other. Why? Because the bonus that an individual gets, that an employee gets, is always a percentage of his fixed compensation, right? So his bonus will always be a function of his compensation. The incentive bracket where he falls is always a function again of his compensation. So higher the compensation of an individual is, higher will be the bonus, higher will be the incentives, because it is assumed that he is on a greater hierarchy. So obviously, if I use these three variables together in the same model, that is where a few of these two variables would lose their explanatory capabilities, because each of these independent variables are dependent on each of them. Let's say employee compensation. Now, employee compensation is not dependent on bonus, but bonus is a function of employee compensation. Hence, if I incorporate both employee compensation and bonus in the same model, there will be a linear association between these variables. And this linear association among variables is known by the name of multicollinearity. So multicollinearity among is a linear association among independent variables, right? Is a relationship among independent variables, whereby movement in one variable helps us explain the movement in another variable, and that is where these concerns, these issues come up, right? Hence, multicollinearity is a problem which needs to be solved, because in the presence of multicollinearity, there can be some variables which lose out their explanatory capabilities. So basically what I will tell you is, you would see that if you use employee compensation, bonus and incentive as three variables of a given model, right, to model some dependent variable, you will see that the T statistic of employee compensation becomes very significant. It's highly significant, while that of bonus and incentives will not be significant, or there is a high chance that they would not be statistically significant, right? So this problem of multicollinearity is something which needs to be addressed at the stage of model development. So we do a check on the multicollinearity, right? So the next thing that we'll talk about over here is multicollinearity, the ways of addressing multicollinearity and ways of capturing multicollinearity as well. Because the testing results of the significance of the parameters of the model depends a lot on assessing the multicollinearity in the regression model, right? Okay.
This conference will now be recorded.
Okay. So, as we were discussing, right? So, okay. So as we discussed that multicollinearity is the linear association between the variables, and in a multiple linear regression model where there are multiple variables, right? Multiple explanatory variables. So in such a framework, it's very difficult for us to, so it becomes difficult to kind of disentangle the impacts of the variables, and they tend to get nearly associated with each other. So what we generally need to do is we need to take care of these issues and multiple linear, and this linear association between the variable needs to be explored. So assessing multiple linearity becomes a very important factor. So let's take up multicollinearity. Let's look into the ways it is identified and the way this can be treated to ensure that all the variables that we have with us in our final model are such that they are independent of each other, right? Such that one does not explain the other. Now, in a real time, in a real world, it is absolutely difficult to get a multicollinearity value of 0. So there are certain tolerable limits of multicollinearity which we need to assess. So, so over here, one of the important topics that we have for so let's first start by defining multicollinearity, and before defining multicollinearity, let us talk about the concept of a linear combination. Let's talk about linear association. talk about linear combination association. So let's say there is a variable z which is explained by delta 0 x1 plus delta 1 x2 xn minus 1. Now this will be now z. I'll say that z is a linear combination of all x1, x2, xn if the following conditions hold. That delta 0, delta 1, delta n is not equal to 0, and summation of delta i's is equal to 1. So the objective of a linear association is that what I'm saying is that this z that I have with me can be expressed as a sum product of these x's and these deltas, right? So that is what the z is all about. Now after this, the next question that comes out to us is the following. Now, how does this roll down to multicollinearity? If this is a linear association among the variables, how do I explain it in terms of multicollinearity? Okay. So let's say there is a variable. So I have a regression equation which I write it as yi is equal to 0. So beta 2 h2i. Okay, so yi is a function of these variables, right, and the parameter coefficients, and the error term. As we know, this error term is nothing but ui follows normal distribution. Sigma square u. So n follows a normal distribution with the mean 0 and a variance sigma square u. Now the next question is that if xi's are linearly associated, what will happen? So over here what I can say is that x1 is a function of delta 0 plus delta 1 x1i delta 2 x2. Sorry, x2i, x3i, so it's delta k x q plus 1. So over here, what we see is that this x1, right, is written as a function of 2i, 3i like this, of all the other variables. So when you write one independent variable as a function of other independent variables, what you call it is the auxiliary regression equation. So we call it the auxiliary regression equation. Right, so this is called the auxiliary regression equation. So what is an auxiliary regression equation once again? So when one independent variable is written as a function of the other independent variables, then that is called an auxiliary regression equation, right? So similarly, 2 can be written as a function of x1, x3 and on the other variables and so on, and this would go on, right? So every time you have a variable, you will do this, and from there you can estimate your uh, whatever your coefficients are. Now, the more significant these coefficients are, the greater these coefficients are, what it means is that a more significant proportion of the overall variation in x1 is being explained by the other variables. So what it means is that if this is a very high variation on x1 which is explained by all the other variables, then what it means is you cannot you need not use x1 as an independent variable. You can use other variables instead. Right? So the auxiliary regression equation will help us assess that what proportion of the overall variation in x1 is being explained by the other variables. So this implies that if any of these explanatory variables are held as constant, then and they are not allowed to change, then x1 self on x1 on its own will not be able to explain significant variations in y height. So hence x1 should not be incorporated in the model. So the auxiliary regression equation gives us an idea of the multicollinearity of a variable with other explanatory variables. Clear? So there are two possibilities over here. all independent variables, or let me put it like this, all xj's explain a significant variation in xi. All xj's cannot explain a significant variation in xi. Var in xi. So over here in this first case, if all the other variables explain a significant variation in xi, then it means xi is dropped. So I don't need to separately keep x1 in this case, because all the other variations, all the other variables are explaining a significant variation in x1. So in such a case, x1 is dropped. So over here what we have is x1 is independent. So x1 is independent and hence is retained back. X is independent and retained. So basically, let's say you develop a regression model and you see that one of the important variables or one of the variables, the group of important variables become irrelevant or they become insignificant. Now, when they become insignificant, what happens is that you know that you cannot keep them anymore. But that's an important variable. Now the question that comes out is to ensure that why is it that they are becoming insignificant? They may become insignificant because of the fact that they have multiple linearity in them. So the next thing that you need to understand is how do we detect multiple linearity, right? So to detect multiple linearity, we would require to understand the concept of variance inflation factor. Now, before I go to talk about the variance inflation factor, we need to understand the key measures, the key overall measures which help us assessing the goodness of fit, right? Because to assess VIO, we would require the understanding of the some of the key overall measures of the goodness of fit of a regression model, right? So so I keep the definition of VIF as an open-end at this point of time. And from assessing the independent significance, statistical independence of the variables, right? What we will do is we will try to move ahead. We'll try to move ahead and assess the overall statistical significance of the variables. right? So we try to assess the overall fit of the model. So what are the parameters that help us assess the overall fit of the model, right? And after this, so once we have explored the overall measures of goodness of fit, we'll come back and we'll talk about VIF. Because VIF uses the concept of R square, right, which is a measure of the overall goodness of fit. So let's start with that part, and from there let's come back and try to understand how to measure multiple linearity. So before we move on to assess the overall goodness of fit measures, now one thing you can clearly see is that when you're talking about multiple linearity, right, I'm trying to talk about an overall goodness of fit, right? So over here, what we are trying to talk about, or what we are trying to understand here is that so first we talk about overall goodness of fit measures for a linear regression model, and from there we'll come back and we'll talk about this. So we apply these measures and see how is it that VIF can be, how is it that multiple linearity can be taken. Okay. Fair. So now we'll start talking about the overall goodness of fit. Now, as we talk about the overall goodness of fit of a regression model. Okay, so before I move on to this overall goodness of fit, uh, so if there are any questions that you have till multicollinearity, you can clarify them, and then I'll move on to talk about the overall goodness of fit.
Sir, in auxiliary regression equation, you have taken
Uh-huh.
dependent variable x1. So you
Right.
can we can take any independent variable here.
Yeah, so auxiliary regression equation, as I said, is the regression of one independent variable on the other independent variables. So over here, what I've done is I have x1 as a dependent variable, and I have seen how is there x2, 3, 4, 5, 6 up to the last k variable. How is it that they explain the variations in x1? Similarly, if you want to know that does x2 have a multicollinearity with the other variables, you take x2 as the dependent variable and all the other independent variables as independent, and you run a regression and you see how is it that this R square, so how is it that the overall variation looks like. So does all the other variable explain a significant proportion of the total variation in x2 and so on. Now, if you see that the most of the other independent variables taken together explains a significantly high proportion of the overall variation of that variable, right? Then you know that that variable need not be used. You can use all the other remaining variables in place of
For every independent variable, we will have to do it separately.
correct.
Okay.
Tanmay, just one question. So in this linear
Uh-huh.
association, you have written that summation of delta is 1.
Uh-huh.
So, suppose this x1 variable is dependent on x2, x3, so x5. So there are so many deltas, delta 0, delta 1, delta 2, delta 3. So I didn't understand one things
No,
that
no,
why
no,
the summation should be
no,
1.
no, no. What I'm saying is, so this is the technical definition of linear association, right? So basically what I'm saying is that Z, so all these x1, x2, the xn's, they comprise together. So each fraction of each of these variable coming together to create Z. So this is a technical definition of linear association, right? Now, when I'm talking about multiple linear regression model over here, that summation delta I equal to 1 need not hold.
Yeah.
So you can skip that. That's a technical definition. That's true.
Yeah.
It's a more stronger definition of linear association. So that can be relaxed in the general cases.
Yeah. Yeah. Okay. Thanks.
Fine. So talking about the overall goodness of fit of a linear regression model. Now, when we talk about the overall goodness of fit, when I want to assess the overall goodness of the model, right? So there are two things which comes into play. Two very important concepts. One is the concept of unexplained variation. Okay, so there are these two parts. One is an unexplained variation. The other is an explained variation. So the other is the explained variation. The explained variation. Now the unexplained variation plus the explained variation taken together will be the total variation. The total variation. Total variation. Right. Now, the overall goodness of fit, a better a model would be when the explained variation is higher relative to the unexplained variation. And this is what we want to know, that how high or how much more is the explained variation relative to the unexplained variation, right? So there are two ways in which we can assess the overall goodness of it. So there are two broad measures which we look into. Number one is the F statistic, the F stat. Now this F stat is responsible to identify that how much of explained variation or what multiple of the unexplained variation is the explained variation. Right? So the F stat is nothing but the explained variation the unexplained variation. Right. So one way to look into the overall goodness of fit measure is that I'm trying to understand that what what multiples of my unexplained variation is my explained variation. And the second important measure is R square. Now this R square is a measure of the explained variation in the model. So over here, the second measure that we look into is the R square. So R square captures the total proportion of the proportion of the total variation which can be captured by the model, right? So so one thing that you can clearly see that when I'm talking about the overall goodness of a model, it is the comparison between the unexplained variations and the explained variations, right? So the next question is to understand how to define. So how to define this explained variation and unexplained variation. So how is it that we can define the explained variation? Variation versus the unexplained variation. The explained variation and the unexplained variation. So that's the next part, right? Now to define these two, to define this explained variation and unexplained variation and total variation, we need to have an understanding of the concept of sum of squares. And it is this sum of squares which has been serving as a measure of the variation. So this is the next part, that it is the sum of squares, right? Now what we need to do is we need to first define this concept of the sum of squares. Now after we have defined the concept of sum of squares, so from there we'll talk about explained, non-explained and all this. So when I say sum of squares, so what do I essentially mean? What I mean is that if there is a variable x, the sum of squares will actually measure its variation from the mean. Right? So this sum of squares is a measure of variation. And when I say variation, the variation here is described as a variation from the mean. So it is measure of variation. It is the measure of variation. And when I talk about this measure of variation, so we need we need to capture both known and unknown variation in our model. And this concept of variation remains very central and similar across all modeling types. So in econometric models, variations refer to variations about the mean, right? So any questions up to this point? Okay, so just check this. So up to this point, is it clear to everyone? Okay, so just go through this. I'll just be back in 2 minutes. Okay, so any questions up to this point?